In this section, we're going to talk about once you know that there is a correlation between two variables, that there is some sort of pattern there, how do you figure out what the pattern is? And so we will use regression to do that. Regression is the actual process of fitting an equation to real data. And so since we're doing linear correlations here, we'll be finding the equation of the straight line that goes through the dots as well as possible. And so because of that, we're going to kind of do a quick crash course review on equations of lines, just in case it's been a while and you're a little rusty on the details of those. So the two key pieces of the equation of a line are the slope and the y-intercept. The y-intercept is the point at which that line crosses the y-axis. So you know the x goes across, the y-axis goes up and down. Wherever it hits that y-axis is the y-intercept. The slope tells you how steep the line is. So every time you go to the right one, how far up does it go? And so that's your slope. You may have heard rise over run, change in y over change in x. They're all different ways of talking about slope. Now we've been talking about positive and negative correlation, so we've actually been skirting around the issue of positive and negative slope already. The positive correlations, as you go to the right, the dots go up. The lines that do that, lines that go up as you go to the right, are lines with positive slopes. And if they go down as you go to the right, then they have negative slopes, just like negative correlations. There are two different ways to identify slopes and y-intercepts. You can do it off a graph of the line itself, or sometimes you have data points or points on the line. So we're going to kind of take a look at both of those ways of looking at this. So on the left we have the information given as a list of points, and so the y-intercept is the point that has a y-coordinate, but for the x it's just 0. So right there at the top you've got your y-intercept of 1, or 0, 1 technically. And then for the slope you have to look at, in this case, the x values are all going up by 1. The slope is, as the x go up by 1, what happens to the y's. So in this case, as your x's go up by 1, the y's are going up by 2. So slope is 2 over 1. If the x's went up by a different amount, you would just divide. So if the x's were going up by 2 and the y's were going up by 4, then it would be 4 over 2. So it's the change in y over the change in x. Or you can look over here at an actual graph and just find the y-intercept on the graph. Here's where it crosses the y-axis. So y-intercept is 0, 1. And then you can count your slopes. So rise over run, change in y over change in x. So you can say, okay, this goes up 2 over 1, 2 over 1, slope of 2. All of that information, the slope and the y-intercept, goes into the equation, and so you're probably familiar with slope-intercept form already. Y equals mx plus b, so y equals the slope times x plus the y-intercept. So in that line that we were looking at, the slope was 2 and the y-intercept was 1, so we would write the equation of that line as y equals 2 times x plus 1. The equation isn't always given to you in the order that you're used to seeing it, however, so here are some to just run through. Pause this a minute and see if you can figure out the slope and y-intercept on each of these. So on this first one, it's in the reverse order. The x comes second, but when you're looking for your slope is always on the x regardless of where it is, as long as the y is by itself. That's actually an important thing there. As long as the y is by itself, the slope is on the x. So in this case the slope would be 3, and then the y-intercept would be the 5, which is the constant. There's no variable there. This form is actually going to be an important one because this is the form statistics people use, so we'll come back to that. The second one's in the normal form that you're used to. The slope is -2, the y-intercept is -3. 3 and 4 you have to be careful because there's information missing. Well, it's missing for a reason. On number 3, there's nothing attached to an x. Well, that means that the slope was actually 0, so the x disappeared. And then the y-intercept is the 17 that you see. Whereas on number 4, it's the other way around. There is a number on an x, so that's your slope, 0.24, and you don't see a y-intercept, so your y-intercept is actually 0 in that case. All right, so that's kind of a quick review of lines. Let's look at how this relates to statistics. So we are looking for regression equations. See, these are sometimes called least squares lines because there's a least squares process for finding them. You won't have to worry about that. The calculator will do it for you. So we're going to put the data in and actually find an equation for the line that best fits that data. It's also called a line of best fit sometimes. So the symbol, you've got y equals mx plus b. That y that we're trying to predict, you plug x's in and predict a y value. That y is y hat when we're talking about a sample. So it'd be a y value if it were population, y hat with a sample. And since our equations are all based on sample data, we'll be using that y hat for all of our equations. This is actually, the regression equation is another piece of information that LinReg t-test spits out. It gave a whole bunch of stuff and the equation is in there. You just have to know where to look. And this is where it's important that I said statistics people write equations of lines backwards. And so they actually write the y-intercept first and then the slope times x. So instead of y equals mx plus b, you'll see the form as y equals a plus bx. That's how LinReg t-test is going to spit this information out. And so you have to be very, very careful with that because you're really used to b standing for the y-intercept. And in this case it's not. B actually stands for the slope. So you kind of have to switch your thinking around a little bit. We're going to use the probability rounding on this. At least 3 significant digits, more if you want to. More would just be more accurate. These are estimates based on a sample, so more accurate would be fine since we're trying to predict things. That works a little bit differently when it's not a decimal, when you're dealing with bigger numbers that have numbers on the left of the decimal point. So when that comes up, we'll talk about it. So let's come back to this car example that we had in the last section and just add on the step with the regression equation. So if you don't still have this in your calculator, pause for a second, go into Stat Edit, put this information back in because we're going to go ahead and pick up and use this to find the regression equation and talk about what that equation means and what you can do with it. So when you do your LinReg t-test, Stat Test, scroll all the way down to LinReg t-test, part of the information that it spits out, you have to scroll down just a little bit to see it, but there was the P, and a couple down from that is the A and then the B. So those are the pieces of information that we need. A is the y-intercept, B is the slope. We're going to round to 3 significant digits. Remember, significant digits are different from decimal places. Significant digits are essentially non-zero digits. It's a little more intricate than that, but we'll just go with that. So, for example, the A value, I start counting digits with the first non-zero number, so the 34 counts as part of that. So I can go 34.7, and that's 3 significant digits. If you want to go farther, that is absolutely okay. But 34.7 would be the minimum number of digits. And then on the slope, the B, I can't start counting till I get past the zeros. So negative 0.00, then I start counting when I get to the 4, 5, 6. So my equation would be y hat equals 34.7, and then that was a negative negative slope, so minus 0.00456 times x. So that's my equation. And it reminds you at the top of the screen what format that equation goes in, where the a and the b go. Don't just write down a and b though, actually write it in equation format. The slope of that equation actually is an important piece of information about the situation. So we were talking about how much a car weighed, that was the x, and then the highway miles per gallon was the y value. So the slope actually tells us that, remember, it's as you go 1 to the right, how far up or down is it going to go? So this says that as you go 1 to the right, you're going to go down 0.00456. That means that based on our sample, we estimate that when the cars get 1 pound heavier, when the X goes up by 1, then the highway miles per gallon will actually decrease by 0.00456 miles per gallon. So as you go 1 to the right, that tells you that it goes 0.00456 down in mileage. That's what your slope tells us. And so that's kind of important information. That's also called the marginal change. Marginal means per unit. We don't usually talk about the y-intercept. You can, but a lot of times because we're dealing with real data, the y-intercept may not be meaningful. For example, the y-intercept tells you the highway miles per gallon if the car weighed 0. And in real life, it's just not practical to have a car that weighs 0 pounds. So a lot of times that's why we don't talk so much about the y-intercepts. Now, as long as your p-value has indicated that there is a correlation, then you can use this equation to make predictions about cars that were not in the data set. So predict the highway miles per gallon for a car that weighs 3,000 pounds. Well, the weights were the x values, so I can just plug that 3,000 in to my equation and get an estimate. So that's what I've done here. I've plugged in the 3,000. And we're going to round our predictions at least as far as the original Y data. You can go farther if you want, but at least as far as the original Y data. So those were whole numbers. I went to 1 decimal place here. So 21.0 or just 21 miles per gallon. Now that is just an estimate, right? Because we didn't have a car that weighed 3,000 pounds in there, and in fact if you took a weight that was in that list and plug it in, you probably won't get the same miles per gallon that the car really had. It's because this is an estimate, and remember this line is just kind of going through dots that don't line up perfectly. So it's an estimate, and it's an estimate based on sample data. You can actually do a confidence interval on these estimates. It's called a prediction interval instead of a confidence interval, but you can actually do that, and it'll say, okay, based on this estimate of 21 miles per gallon, we actually think that in the population, cars that weigh 3,000 pounds would be somewhere between 18 and 24. We're not going to do that in this class only because it does not come preloaded on your calculator. I can give you that program in person if anyone is interested, but just because of the difficulties of getting that program to you, we'll leave that out. But do know that that is possible to actually find an interval in which you expect actual cars in the population to fall.